So thank you all for coming here. We're pleased to have Huzaifa here with us, talking about an open testbed to enable extended reality systems research. So Huzaifa is a PhD candidate in computer science at the University of Illinois, Urbana-Champaign, where he works with Professor Sarita Advai on systems and architectures for extended reality. Together with his advisor, he leads the ILLIXR project. I hope I'm pronouncing it right. And he co-chairs the ILLIXR Consortium. He's also a recipient of an IEEE Micro Top Picks and IISWC Best Paper Award, the Suhaib and Sarah Abbasi Computer Science Fellowship, a Feng Chen Memorial Award, and an Outstanding Teaching Assistant Award. He holds a Bachelor of Engineering in Computer Engineering from McGill University. So I'll let Huzaifa take the stage and take it away.
Thank you for that introduction, Umar. So yes, you were pronouncing it correctly. It is ILLIXR. It stands for the Illinois Extended Reality Testbed. So the motivation behind this work is that we live in an era of specialization. By specialization, I mean hardware specialization. And what that means is that if you look at modern system on chips, such as the one shown here on the left, which is an Apple A12, so relatively recent chip, you will notice that it has a lot of hardware IP in addition to what you would usually expect. So people think of just CPUs and GPUs, but these SoCs have neural network accelerators, Wi-Fi, LTE, audio, video, touchscreen accelerators, and so on and so forth. And this graph here shows that since such chips started coming out, there has basically been an explosion of these accelerators, and we're at give or take 3 dozen, and this number is actually expected to increase. And there has been a lot of research recently on how to design these specialized accelerators. However, moving forward, the question is not about how we design individual accelerators. Instead, it's about how do we design entire specialized systems. What that means is it's not only just about these individual accelerators, but also how they communicate with each other, what's the software that's going to run on top of these hardware IPs, and what are the applications going to look like and how we optimize them for any given piece of hardware. These applications have basically led to the rise of edge computing. That includes augmented and virtual reality, robotics, autonomous vehicles, and several other domains. And what is really interesting about these applications is that they have really challenging performance demands. So much more so than what we're used to in a regular desktop or a smartphone. They also have much more stringent resource constraints. So as opposed to using hundreds of watts or tens of watts, these applications require watts, or in the case of augmented reality, just several hundred milliwatts of power budget. And there are end-to-end quality metrics, such as how good the audio is, are the graphics good, does the card not crash, and so on and so forth. And so when we combine this era of hardware specialization with these emerging applications, what that requires is what we call scalable and generalizable system specialization. By scalable, we mean 2 things. One of them is the more resources you throw at the system, the higher the quality should be. It should not be the case that you have better and better hardware, but the quality is still the same. They both should scale at roughly the same rate. And similarly, the more time you spend in actually optimizing your hardware and software stack, that should give you better, or that should enable more and better application features. That could include just higher resolution, better frame rates, better graphics, and so on. By generalization or generalizable, what we mean is that this should not be done for just one particular small kernel in isolation. This should be for an entire application domain. So it should be application driven, it should be quality driven, and you should co-design the entire stack. And so you come up with these techniques that are applicable to more than one domain, and then you just put in the engineering effort and you design these custom systems. And then these systems are what we envision would be commonplace 10 years from now, give or take. The question though is, how do you do this research? What application should you choose so that you can come up with scalable and generalizable system specialization techniques? Our answer to that question was XR, or extended reality, which is an umbrella term that we use for virtual, augmented, and mixed reality. So just all these different types of modalities that are out there. And this is largely believed to be the next computing interface. This is going to replace smartphones. And the idea is augmented reality glasses will replace smartphones. Virtual reality might replace desktop computers and so on. And it'll impact practically all aspects of our lives, the way we do science, medicine, how we teach people, how we interact online, and so on and so forth. The problem with XR, though, is that there's an orders of magnitude gap in power, performance, and quality of experience between the systems that exist today on the market and the systems of the future that we really want. There are many dimensions along which this gap exists, but I'll just highlight a few here. If you look at resolution, current devices are at about give or take 7 megapixels, whereas if you want to fool the human eye that what it's looking at is real in a virtual environment, you need about 200 megapixels or so. For power, again, the power envelope is give or take 7 watts for modern devices. If you want all-day wearable augmented reality glasses, it actually has to be just about 100 milliwatts or so. Weight is a pretty constraining factor. These devices are heavy. You can't really use them for more than 30, 40 minutes, maybe an hour. If you want all-day wearable devices, they have to weigh as much as regular glasses do, which is usually just tens of grams. And then when you look at other dimensions as well, such as field of view, frame rate, fidelity of audio, we are literally talking about 1,000x or 10,000x gap between what exists today and what we would like to exist in the future. So these challenges are not unique to XR per se. You could look at micro-aerial vehicles, drones, autonomous cars, and they all have very severe performance and power constraints. But what makes XR challenging is quite a few other things as well. One of them is that it requires expertise in quite a few sub-areas. So there's graphics, audio, video, haptics, optics, and so on. And in order to build this specialized system, you really need to know what's going on in each of these individual domains. Next, it's not like XR is just a software problem or a hardware problem or just an operating systems or a compiler's problem. It actually spans the entire stack. So you have to be familiar with all of these different parts of the system stack and be able to co-design them together. Next, there are not only complex metrics, there are many of them. As a very simple example, it is very hard to gauge the goodness of the visual quality, basically, because understanding the human visual system is still an open area of research. We have made a lot of progress over the past 40, 50 years, but we still can't quantitatively say how a human will perceive any given image. So these are very complex metrics, and there's more than one of them. There's one for the visual system, there's one for audio, and then within each of these, there are multiple submetrics that you have to look at and then optimize together. And then the big one is that before we started this research, there were no open source systems that we could actually look at. Yes, there are products on the market, but they're closed source. You cannot look at their source code. You cannot make any modifications to them. There are no benchmarks. There's no standardization of any kind that you could look at. So if you wanted to build these systems of 2030 and you wanted to use extended reality as a driving domain, there was a large barrier to entry. And so then we asked the question, how can we democratize XR systems, research development, and benchmarking? And that is when we developed ILLIXR, or the Illinois Extended Reality Testbed, which is the world's first fully open source, full system XR testbed. It includes several state-of-the-art XR components with a modular runtime. And we have extensively characterized this and are now using it, and so are many others actually, for computer architecture and systems research. And if you want to know more, there's a lot more detail, our paper, actually this slide deck, quite a few demos at illixr.org. So before I dive into what exactly ILLIXR is and what it does, I will actually like to show you a few of these demos. This will be pretty choppy, I'm assuming, on your end, because Zoom isn't really good at transmitting video. So you'll just have to take my word for it that it's smooth. It's not very jittery. So what's happening here is I am holding a camera, which basically is emulating a headset, and then walking around in my lab. And you can see what the camera is seeing here at the bottom right. It's a stereo camera, so left and right cameras working together, and you can see those images here. In the middle here is a third-person view of the virtual environment in which I am immersed in. So we've just built a simple environment called the ILLIXR room. And then in this room, you can see the headset. And on the right side, we have the actual stereoscopic display that I was seeing in that instant. And what this demo is meant to show you is that ILLIXR is a real system that runs on real hardware today. It tracks pretty well. So we're actually doing head tracking using the camera and the IMU. We're actually in charge of rendering all of these pixels. And then here on the left, you can see what we call a debug view, which gives you a lot more information about what's happening inside the system. Then we have this other demo where we're running an actual application. And so you will see this very interesting setup that we have with Joseph using the headset. And then we have Jeffrey basically rolling this beefy desktop behind him because, like I said, right, there's a huge gap between what XR can do today and what we wanted to do. And that includes the power gap. So you can power these experiences, but they require these big desktop machines, which burn 200, 300, 400 watts. And so if you want mobility with that, what you then would like is somebody like Jeffrey rolling around a PC behind you all the time. And you can see that it works pretty well. Again, it's pretty good graphics, tracking works well, and Joseph is doing his own thing. But of course, if you don't happen to have a Jeffrey, you don't have a trolley, then you can use one of these backpacks that HP makes, which is shown here. So now Joseph is wearing that and is now able to move freely. These backpacks, though modular, still burn about 100 to 200 watts, so their batteries don't last very long. And of course, our end goal is to not require people to wear these backpacks and instead just wear the standalone headset and move around as they wish. Alrighty, so in addition to actually doing all of this research, we have also launched the ILLIXR Consortium, which is an industry-backed consortium along with several academic partners. The companies include ARM, Meta, Micron, NVIDIA, and a few others. The goal of this consortium is to actually make ILLIXR an open source reference testbed that people can use to both develop new XR techniques and benchmark existing ones. And so the idea here is that if you go on the market today, and if you look at two VR headsets, let's say an Oculus or a Meta Quest 2 and an HTC Vive Pro, for instance, there's no easy way to compare the two without actually trying both of them on. As part of the ILLIXR Consortium, we want to standardize what is measured and how it is measured. So that's the benchmarking part. And we want to give people this open source runtime, this open source testbed, so that they can change it however they want, develop new techniques, and so on. And again, you can find out more at illixr.org. If you want to get in touch with us, we have a Discord. You can email us. And we actually have weekly open meetings, Wednesdays at 11 a.m. Central. All the info is at illixr.org, including the Zoom link, where basically people from industry and academia come and give talks on what they're working on in XR and how they want to use ILLIXR and actually contribute to it. Okay, so what is ILLIXR? This is an overview of the entire system when somebody is running an extended reality application. We, of course, have the application on top, which is usually written using a game engine such as Unity or Unreal or Godot. And then this game engine or this application then has to interface with the XR runtime. There is a new interface for that called OpenXR, and there's an implementation of OpenXR called Monado that we leverage. And then we move on to this runtime in the middle, which is ILLIXR. ILLIXR consists of three pipelines: perception, visual, and audio pipelines. The perception pipeline deals with figuring out what the user is doing. This includes things like head tracking, eye tracking, scene reconstruction, processing camera images, and so on. The visual pipeline is responsible for generating the pixels that the user will see, and the audio pipeline is responsible for generating the sound that the user will hear. All three of these pipelines are composed of individual components that are running on their own. So they could be their own threads, or they could be fused together into an individual thread. And they all communicate together via ILLIXR's communication interface and runtime, which we call switchboard. And then underneath ILLIXR is the actual mobile device, which could be a desktop, a laptop, an embedded board, or whatever else that you wish to use. So I'll go over the pipelines now one by one. First, in the perception pipeline, we have support for different sensors, different types of cameras, and IMUs, which stand for inertial measurement units. So these are composed of two things: an accelerometer, which gives you linear acceleration along 3 axes, x, y, and z, and a gyroscope, which gives you angular velocity, again, along 3 axes, x, y, and z. There are different types of cameras. There are infrared cameras, depth cameras, colored cameras, grayscale cameras, and we have support for quite a few inside ILLIXR. The information from the cameras and the inertial measurement unit is passed on to a component called visual inertial odometry, which is colloquially known as head tracking, and as the name implies, it is responsible for providing the position and orientation of the user's head, which we call the pose. Here you see an example of a camera image, which has been annotated with the features that the visual inertial odometry component is tracking in that particular instant. VIO is usually very accurate, but the problem is that it runs at camera frame rate, which is usually between 10 to 30 hertz, which is okay if you're sitting around, but it's not really good when you're either running or if you have very fast head movements. As an example, the human neck can easily do about 500 degrees per second. And if you are capturing that at 30 hertz, there will be large gaps. You won't be able to immediately perceive the head rotation. And so to make sure that we always know where the user is, we make use of an IMU integrator. This provides high frequency pose estimates at the frequency of the IMU, which is about 500 hertz to about 1 kilohertz. So much, much faster than the camera, and is then definitely able to capture the user's head movement. So the IMU integrator is less accurate than VIO, but is faster. VIO is more accurate, but it's slower. We use the two of them together to get both high frequency, high speed pose estimates. However, you don't always want to know where the user is at any given instant. Sometimes you wish to know where they will be sometime into the future. This is typically useful if you're, for instance, cloud rendering, and you know there will be some delay by the time the frame will be displayed. In fact, there's also delays when you're doing on-device rendering. And so let's say you're going to display the image 20 milliseconds from now. You can predict the pose 20 milliseconds into the future by using a simple linear acceleration or linear velocity model. Moving on, we have a scene reconstruction component, which is responsible for building a 3D map of the world around the user. Here you can see a reconstruction. This is actually not a picture. This is a real reconstruction of a lab space. And as you can see, it's pretty good. You can make out the furniture, the mouse, keyboard, monitor, the backpack on the ground, and so on. And the final thing that we have in the perception pipeline is the eye tracking component, which is responsible, which requires 2 cameras that are pointed towards the user's eyes. And then we figure out exactly where on the screen the user is looking. And this has various uses. For instance, you could use this for scrolling. You could use it as an input. And then certain graphics techniques require eye tracking information. Moving on to the visual pipeline, the first component that we have is something called asynchronous reprojection, but this is more colloquially known as time warp. It's a term that Oculus, now Meta, popularized. Everybody calls it time warp, but the actual term is asynchronous reprojection. And the idea here is that when you start rendering a frame, right, when you start generating the pixels that will show up on screen, it's not instantaneous. It takes a little bit of time. Let's say it takes 10 milliseconds. What's going to happen in those 10 milliseconds is that the user's head might have moved. And because the user's head has moved, the perspective of the image now has to, or the perspective of the scene now has to be changed. Of course, you cannot keep re-rendering infinitely. So the solution is you take the rendered image and you rotate it such that it is from the new vantage point. And this actually uses pose information, and this reduces what is called motion to photon latency, which is a very common metric that is used to measure the goodness of XR systems. What it means is it measures the latency between a user doing a motion and the photons corresponding to that motion entering the user's eyes. For virtual reality, this acceptable latency is about 20 milliseconds. For augmented reality, it's between 5 and 7 milliseconds. So this has to be very, very low. And this is a very real-time system. The next component is something called lens distortion and chromatic aberration correction. The optics of modern XR devices use these very thick and curved lenses. And one of the side effects of using these lenses is that they really curve the incoming light. So straight lines don't remain straight anymore, and white light actually gets split apart into the individual RGB spectrum of the LCD display. And so if you want to present the correct image to the user, what you have to do is you have to apply a reverse distortion of what the lens is going to do. Then the distortion cancels itself out once the light passes through the lens, and you get the rectified image as shown here. And finally, there is a common problem in modern headsets called divergence accommodation conflict, which is actually illustrated here. Hopefully the picture is, you can make out what's happening. When you look at something, there's basically two things that happen. One of them is that wherever you're looking, the lens in your eyes, it accommodates, or it expands or contracts so that it focuses on that point. So that is accommodation. The other thing that happens is that your eyeballs rotate out or inwards such that they converge at, again, wherever you are looking. That is called the divergence or the convergence point. And in real life, both of these points are exactly the same. They're always the same, and they have been since the day you were born, of course. What is interesting is that this is not actually a hard requirement for the brain. The brain can actually function if the 2 points are different. But because the brain is only used to them being always the same in real life, when they are different, the brain perceives them as fatigue. And as so happens, they actually are different in XR head-mounted displays. The reason for that is you basically have a screen that's just right in your face, and you have some lens which projects the light from that screen at some fixed focal distance. So now you have varying depth in the scene, right? You want to look at stuff that's close to you, that's far away from you, but the focal length of the lens is fixed. And so the divergence point and the accommodation point then become different, and people perceive this as actually subconscious fatigue or eye strain, and in some cases it can cause headaches and so on. And there are many ways to fix this. One possible solution is something called computational holography, which generates this per pixel phase mask, which modulates the individual pixels in a particular way, which gives you the illusion that you have infinitely many focal planes, just like you do in real life. And so ILLIXR provides that capability. And finally, in the audio pipeline, we have two components. The first one is audio encoding, which encodes individual sound sources into a virtual sound field called a higher order ambisonic sound field. The idea here is, this is a mathematical representation. So you imagine that there's a user and there's a unit sphere around the user, and you have some number of virtual speakers on the surface of the sphere. And then this representation is mathematically very elegant. It allows for very simple and easy manipulation of the individual speakers. So going from real sound sources to these virtual ones is the job of the audio encoding component. The reverse of this is the audio playback component, which basically one is responsible for manipulating the sound field. So for instance, if I'm wearing a pair of headphones, and I rotate my head, that would be the equivalent of rotating the sound field. And if I move backwards and forwards, that's equivalent to zooming in or out of the sound field. So playback does that. And then it maps from these virtual speakers. Let's say you have 16 virtual speakers, but you're wearing a pair of headphones. So those 16 have to be mapped to the 2 physical ones. That process is called binauralization. And it's actually a pretty interesting thing because the way spatial audio works in real life is that there's many, many cues. One of the more interesting ones is that when we are hearing something, so you guys are listening to me right now, for instance, right? And you know that the sound is coming from a particular direction, wherever the speakers are. And the way you know that is when the sound actually hits your face, it gets changed by the shape of your face, your nose, especially your outer ear. And the brain actually uses that information to pinpoint exactly where the sound is coming from. And that's why even when our eyes are closed, we know where people are standing if they're talking. So the audio playback component is responsible for making sure that all of these effects also take place in whatever virtual world that you are immersed in. But XR is not just a collection of these individual components that I went over. It is a system in which all of these components exist together and are running together. So to take an example of the data flow that occurs, we have the IMU component, which is running at a particular higher frequency. So let's say between 500 and 1000 hertz. We have the camera, which is running at a much lower frequency, 10 to 30 hertz. And then we have the VIO component, head tracking, which takes information from both the IMU and the camera. You will see that there's 2 types of edges here. There's a solid one and there's a dashed one. A solid one represents a synchronous dependency. What that means is every time the camera publishes an image or generates an image, VIO has to run and consume that image. The dashed one represents an asynchronous dependency. What that means is every time the IMU generates some data, VIO does not have to run. VIO can run whenever it wants. It will just take whatever the latest IMU value available is. We have the IMU integrator, which reads from both the IMU and VIO. We have eye tracking, which is running on its own. We have scene reconstruction, again, running on its own, and typically uses a different camera than VIO. And then we have the application, right? That's the thing that the software developers at the game engine level wrote, which looks at the pose information, eye tracking information, the scene reconstruction, and then generates the actual imagery. That imagery then gets passed to reprojection along with the pose of the user, which then gives the final frame to hologram, which then puts it on the actual display. We have recording going on, and in parallel, we can have playback, which also needs the pose in order to manipulate the virtual sound field. So there's a lot of components. They're running at different frequencies. They have different dependencies between them. There are several pipelines running in parallel. And each of these pipelines or sub-pipelines have different quality of experience metrics that the runtime somehow needs to handle. And so the ILLIXR runtime, which we call switchboard, uses a modular and flexible architecture for the individual components. What that means is that each component is actually compiled and loaded separately. So the build system is actually quite simple. You don't have this monolithic thing where everything has to be compiled together. Let's say you have baseline ILLIXR, and for instance, we don't have hand tracking right now. And let's say you come along and you want to build your own hand tracking component and contribute it to ILLIXR. You can actually develop almost all of it in isolation without looking at anybody else, because the build system will be separate. All you will do is you will generate this shared library, which then the ILLIXR runtime will load at runtime. And at that point, it can start communicating with the other components. And so this modular architecture allows for easily swapping one component for another, changing a particular implementation for another one. In terms of communication, we use named event streams and a publish and subscribe model. So for instance, there could be a stream called camera, and camera publishes to that stream. VIO can subscribe to that stream. Whenever something gets published, VIO will automatically get invoked by switchboard. We support both synchronous and asynchronous dependencies, and all of this is implemented using shared memory. So there's no copies, and this implementation is fairly performant with practically no measurable overhead. And so there were many ways to design this runtime, but we believe that our particular architecture balances flexibility with efficiency. Now, looking at applications, there are two ways of writing applications that use ILLIXR. One of them is to directly interface with the runtime. This is historically how applications were written, for instance, using Oculus VR runtime, Windows Mixed Reality runtime, Steam VR, or something else. But the problem with that was there was a lot of fragmentation. If you were a game developer who wanted to support 5 different platforms, you would actually have 5 different releases of your game, which is a lot of work. And so the industry came together and came up with this new standard called OpenXR, which is a standard interface between applications and runtimes. And there's an open source project called Monado, which provides a reference OpenXR implementation. That is what we use with ILLIXR. And what that allows us to do is any game engine that supports OpenXR implicitly also supports ILLIXR. We already have support for the Unreal and Godot game engines. And hopefully soon we also get it for Unity, at which point we will support all of the major game engines that are out there in the XR market. And finally, ILLIXR supports the ILLIXR Runtime switchboard supports a lot of quality metrics. These include motion to photon latencies. So as I mentioned before, the time from head motion to display. This is currently without the display latency because there's no easy or standardized way of measuring display latencies because they really vary from display to display. We have 2 different types of image quality metrics and then excessive telemetry, including frame rates, dropped frames, how much power was consumed, time distributions, pose error, scene reconstruction error, and so on. And so this here is a recap of all of the components that we talked about in the different pipelines and the various implementations that exist in the ILLIXR ecosystem today. And we support both desktop PCs and laptops, as well as embedded boards such as the NVIDIA Jetson Xavier. I will now give a quick, actually before that, any questions so far? Okay. So I will now give a quick summary of the results that we have obtained from ILLIXR. These include the frame rates of the different components in the different pipelines on different pieces of hardware. So desktop, a high performance embedded board, a low performance, a low power embedded board, time distributions, whether you were meeting your deadlines, what the variation in execution time was for each component on a frame to frame basis, where do the CPU cycles go in the system, what is the power breakdown, both in terms of components and in terms of hardware. What the quality of experience is using the motion to photon latency and the various image quality metrics that we have. And altogether, these are the first published performance, power, and QoE results of an end-to-end XR system. And if you're curious about the actual details, you can find them in our paper, which is available on illixr.org or on IEEE Explore, I guess, at this point too. And so based off of these results, we came up with several implications for system designers, people who want to design these systems for 2030. And so these exist for both individual components and at the system level. And so what these results showed was that ILLIXR actually provides a rich playground for doing systems research. It has enough diversity of tasks, of components that you can do OS research, scheduling research, hardware research, software research, application research, and so on and so forth. And in fact, I will be highlighting some of the research projects that we or others in the architecture community are working on using ILLIXR. One of the first things that we started doing was looking at intermediate representations for ILLIXR. And so right now, everything is LLVM based, which is an inherently sequential intermediate representation. So you can't really capture any type of hash level parallelism, data level parallelism, nested parallelism, and so on. There's a work called HPVM, or the Heterogeneous Parallel Virtual Machine from Illinois, that is actually able to capture all of these different types of parallelisms, and we are porting ILLIXR components one by one to this. And once we have this, better view of the software at the compiler level, we can actually automatically generate accelerators, we can generate code, we can perform approximations, resource mapping, and these are all things that we would like to explore in the future. One such thing that we have already done is the automatic selection and generation of accelerator hardware using ILLIXR represented, or a subset of ILLIXR represented in HPVM. What we showed was you can still do this using LLVM, but because you don't have this notion of parallelism in LLVM, the hardware is less efficient than it could be. So when you use HPVM, we actually showed a 2x better performance for the same area compared to using a sequential LLVM representation. And moving forward, we can do compiler analyses to find common patterns because there's just a huge diversity of tasks inside ILLIXR, and developing a unique piece of hardware for each component is not going to be possible. So we have to find these common compute and memory patterns, and writing compiler passes on top of HPVM will actually enable that. Another thing we're working on are building communication interfaces between accelerators. As I mentioned at the beginning of my talk, modern SoCs now contain upwards of 40 individual accelerators. Unfortunately, they still communicate via main memory using DMAs, which is not as efficient as doing on-chip communication. But doing on-chip communication comes with its own sets of problems and challenges, and we are trying to actually solve those using a work called Spandex, which was developed by our group, and using XR as the driving workload. We are also looking at cross-component co-design in various ways. One of them is we're looking at scene reconstruction along with other components. And this is a work in progress. And what we have shown so far is that if you look at components in isolation, which is how people unfortunately do research today, because before ILLIXR, there actually was no open source full end-to-end system, right? Is you actually miss out on opportunities for optimization. So when you look at more than one component together, there are interesting things that pop up, which when exploited can give you performance benefits, power benefits. The other one we're looking at is eye tracking and foveated rendering together. So eye tracking, I already explained before. Foveated rendering is basically a technique which generates pixels in such a way that mimics the human visual system. And so again, these two are usually developed independently. What we're doing is we're looking at both of them together and are coming up with approximation opportunities that otherwise would not have been possible. We are also looking at performing QoE-driven scheduling of all of the components that exist inside ILLIXR, including hardware mapping if you have more than one hardware choice for a given component. So a common example is you can either run on a CPU or a GPU or a DSP. Which one do you choose at runtime based off of what's going on in the system is an open question. And so we're working towards that. Some preliminary results that we have show that we can do then baseline Linux scheduling, at least on a single core CPU, and we're now extending this to multi-core CPUs. The next big thrust in ILLIXR actually is moving from a single device, which is what ILLIXR is right now. ILLIXR right now represents an individual head-mounted display or an individual augmented reality glasses. But there's no need for that, actually. One, because running all of the components in 100 milliwatts or so is just not going to be possible, no matter how much hardware acceleration you do. And number two, there actually is no need to do everything on the device itself, because there are several components which are latency tolerant and can be offloaded to either an edge server or to the cloud itself. And so we are now changing ILLIXR such that it supports offloading to the edge and to the cloud, and that it also supports multi-party XR experiences. And this is work that's in collaboration with Arena, which is a project out of CMU, which supports distributed XR and multi-party XR. And there's actually several other projects that either we are doing or others are doing. So eye tracking holograms was a project from Penn State. There's a professor at University of Washington who's using ILLIXR for security and privacy research. There's others at UIUC who are looking at 360 video streaming. We ourselves are looking at on-sensor computing, and there's just a whole bunch of stuff that ILLIXR is being used for. That was the research side of things. Just very quickly, we're also expanding both the testbed and the consortium. So testbed includes more components, offloading, more platform support, more data sets, better applications, and then of course incorporating research results back into ILLIXR. And on the consortium, and we actually are now starting to form working groups on various topics. So a topic example could be metrics. Another topic could be rendering. So we're actually getting the community together. We have, again, as I mentioned, these open meetings, Wednesdays at 11 a.m., where people show up and present. And we are now actually working towards our vision of making ILLIXR into this open source testbed and benchmarking methodology. That's the end of my talk. For a lot more details, things that I skipped over, you can just go to illixr.org to find the paper, the presentation, some more demos, information about our Discord and the weekly meetings. And before I take questions, I would like to point out that this was a huge multi-year effort, including my advisor, Sarita Adbe, without whom this would, of course, not be possible. And then a lot of undergrads and grads at UIUC and many consultations with both academia and industry. Thank you.